Hello students, welcome to another lecture. In this lecture we are going to talk about another technique for characterization of material, which is called dynamic light scattering. So we're going to discuss what we can measure with dynamic light scattering and how this technique works, what is the working operation, and what data we can get using dynamic light scattering. So first of all, DLS, dynamic light scattering, is a technique that is used in physics and also chemistry and also nanotechnology, and it is used to determine the size distribution of small particles that are suspended in a solution. So you can say that our sample with dynamic light scattering is not a solid sample, is not a powder, but it's a solution that we have some particles suspended in this solution. So let's say, for example, we have some gold nanoparticles that we have synthesized, and these gold nanoparticles are suspended in a colloid solution. We can actually use that solution sample and analyze it using a dynamic light scattering to see what is the size of those particles. And in this case, we are measuring the size distribution of those small particles, which in our case is gold nanoparticles that are suspended in a solution. So this technique is based on the fact that when a beam of light passes through a colloid solution, the particles will scatter light in all directions. So this is the fundamental um, working process that we are using to measure the size distribution of small particles. Now we have to keep in mind that as you listened in previous lectures, in each of these techniques, we are using some source of illumination. For example, X-ray beams, it could be IR arrays, it could be light, it could be electrons. In this case, we are actually using light. The source of illumination is light. The data that we get is size distribution of small particles that are suspended in a solution. So particles that are dispersed in a solvent are in constant motion because of the Brownian motion. So the Brownian motion of particles, which this technique is based on, it means that particles that are dispersed or suspended in a solvent are in constant motion. They are moving all the times. So small molecules move faster compared to heavier ones. And that is kind of the basic and fundamentals that is used in this instrument to measure the size distribution. Brownian motion is particles suspended in a solution are in constant motion, and small particles move faster and larger particles move slowly. Now, the source of illumination, as we mentioned, is light, is actually a laser, which is concentrated light. When we are exposing that sample solution, let's say we have some gold nanoparticles. This is a cuvette, a glass cuvette that um, we use in the dynamic light scattering, and we have some gold nanoparticles that are distributed in our solution. Now we use the source of illumination is a laser, And when laser is exposed to these particles will scatter light in all directions. The thing is, these particles are in constant movement. They are constantly moving. So when you use this laser in different time frames, for example, time 0, time 1 second, you repeat this process, you get a different scattering light. So the detector is actually detecting and comparing the fluctuation in the scattering light, which is measured in different time frames. Now we have different type of scattering. For example, Rayleigh scattering. This is when particles are smaller than the wavelength of light that we are using. Scattered is done in a uniform way in all direction. And also the May scattering, which the particles that are being measured are bigger or larger than 250 nanometers. So the technique that we discussed is dynamic light scattering, and the instrument that uses this DLS technique to measure the size of particle is called Zeta potential sizer. So Zeta potential sizer uses the DLS dynamic light scattering technique to measure the size of particle. So the question is, what is actually being recorded using the Zeta potential sizer? And the answer to this question is the instrument actually records and reports the hydrodynamic diameter of a particle. So we're going to discuss the hydrodynamic diameter in more details later, but just to know, the hydrodynamic diameter is the diameter of a particle that moves with the same speed as the particle that is being measured. For example, if the instrument records that the hydrodynamic diameter of this particle is 10 nanometer, it means that this particle is moving with the same speed as a particle that has a diameter of 10 nanometer would move. So the hydrodynamic diameter is the size of a particle that moves with the same speed as the particle that is being measured. There are several parameters that will affect the hydrodynamic diameter, and these parameters are included in the Stokes-Einstein equation. One of them is viscosity of the solution. This technique is based on the Brownian motion of particles. We know that the viscosity of solution will affect with what speed the particles are moving. If we have a very viscous solution, the particles will move slower. So we have to take into consideration the viscosity of the solution when we are measuring the dH, the hydrodynamic diameter. Another parameter is temperature. Again, the temperature of the solution will affect how the particles, with what speed the particles are moving. And another parameter which is called DT, translational diffusion coefficient, which we will. So what is the working operation of dynamic light scattering? In the DLS technique, we have a monochromatic light, which is a laser, a focused light, such as laser. We have our sample, which, as I mentioned, the sample is a solution that particles are suspended in. The solution is a colloid solution. A colloid solution is a sample that particles are dispersed in a solution and they are not dissolved in that solution. One example is gold nanoparticle, which is a colloid solution. And once laser is exposed to these particles will scatter light in all directions. And the detector, which is a photon counting detector, will detect this scattered light in one of those directions, and it will give us a graph. The final graph that we get using a dynamic light scattering will look like this. We have intensity in the y axis, and we have diameter here. And as I mentioned, a size distribution of particles distributed in a sample, and that's what we can measure. So the graph will look like this. So this is actually telling us if, for example, this is 100 nanometer, that this sample, the majority of the particles have a size of 100 nanometer, and there's a size distribution of other diameters as well. So what we get is actually a size distribution of what is the major size of the particles and what are the other sizes of our sample with what percentage. In this technique, laser is shot through a polarizer and into a sample. All molecules that are being hit with the light will diffract light in all directions, and this process is repeated at short time intervals. For example, as I mentioned, time 0, the first laser is shined, time 1 second is repeated, time second 2, this process is repeated. So we are repeating shining this laser light through different short time intervals. And as we mean by short is around millisecond, this process is being repeated. To measure the diffusion speed, the speckle pattern is produced by eliminating the particles. Now we know that the scattering intensity at a specific angle will fluctuate with time, and this is because the particles are in constant motion. The Brownian motion is because these particles are constantly moving, so the scattering intensity at a specific angle will actually fluctuate with time. As I mentioned, in time 0 we have a specific scattering intensity. Time, for example, 1 millisecond, we have another specific scattering. Time 2 millisecond, this scattering intensity is going to be different. The reason is these particles are moving, are in constant motion, and their position with respect to each other is going to change. So how this scattered light is going to get diffracted is going to change as well. The intensity change are analyzed using an autocolorator. That's why the DLS technique is sometimes referred to colorator spectroscopy. But actually, a DLS is a more common name for this technique, but sometimes it's called the colorator spectroscopy. The coloration function curve is to analyze the size and Dynamic light scattering is a non-invasive technique for measuring the size of particle. Actually, is one of the first instruments that when you synthesize a nanoparticle, gold nanoparticle, silver nanoparticle, when your sample is particles that are in solution, one of the first technique that you can use to kind of measure the properties of your sample is the DLS technique or the zeta potential sizer. With this technique, it will give you data such as the size of the particles, and with this data, you can know that if you have actually synthesized nanoparticles or the size of the particles are bigger, or what size distribution your sample has. So we talked about the Brownian motion. The Brownian motion is the random movement of particles due to being bombardment by the solvent molecules. So constant movement of particles. We talked about the DLS technique, dynamic light scattering, which measures the speed of particle, particles undergoing Brownian motion. We discussed how the DLS measures the speed of particles is actually it measures the scattering light in different time intervals. So we know that small particles diffuse and move rapidly because of their size, and larger particles diffuse slowly. So small particles compared to large particles will scatter light differently. The velocity of Brownian motion is defined by translation diffusion coefficient. I'm going to write here translational diffusion coefficient, which is called D. The equation that we have is called the Stokes-Einstein equation. I'm going to write here. The Stokes-Einstein equation is important in the DLS technique is the equation that is being used to analyze the data that we have and convert it into particle size. We have dH here, which is the hydrodynamic diameter. We have K, which K is the Boltzmann constant, is a value that depending on the solvent or solution is going to be constant, and we actually have this value. This is one of our known parameters, times temperature. So temperature is a parameter that is going to affect the movement of particle. If your solution has a high temperature, the particles are going to move faster. If the temperature is if we have a lower temperature, the particles are going to move slowly. So this is a parameter that we have to take into consideration for measuring the size of particles. We have 3 pi nu, which is viscosity. Viscosity is another parameter that will affect how particles, with what speed the particles are moving. And D, which is diffusion coefficient. And this parameter is actually what the instrument is recording, is detecting. The detectors of this instrument is detecting D, and they are converting D with the Stokes-Einstein equation to the hydrodynamic diameter. of that particle. And the final graph is intensity of the scattered light versus the size, the diameter. And we get a graph that is the distribution of these particles, the distribution size of these particles in our sample. Now, if this is like, for example, 200 or 100, we know that the majority of particles have this size. And so let's define the hydrodynamic diameter, the parameter that the DLS measures another time. The diameter of a hard sphere that diffuses at the same speed as the particle or molecule that is being measured is called hydrodynamic diameter. I'm going to write here the diameter of a hard spherical sphere that diffuses at the same speed as a particle or molecule that is being measured. So for example, when the DLS reports or detects that the hydrodynamic diameter of this sphere, for example, is 20 nanometer, it means that this particle is moving at the same speed of a particle that has a diameter of 20 nanometer would move. There are several parameters that will affect the size or the hydrodynamic diameter. A couple of them I'm going to mention. Their ionic strength, the surface structure, also shape. So let's talk about how the ionic strength of a particle will affect the size or the diameter of that particle. So the particles that are charged, they have a cloud of ions on their surface. This cloud could be positive or negative. It will actually determine what is the charge of this particle. So let's say this is a particle that is ionized, and we have a layer of positive charge on the surface of this particle. There is a parameter that is called the Debye length. The Debye length is the thickness of electrical double layer, the cloud of ions that are surrounding a particle. So the Debye length is the thickness of the cloud ions. This parameter is inversely proportional to ionic strength. What that means is that if the ionic strength is high, for example, we have a strong positive layer on this particle, the Debye length is going to be less. So if we have a high ionic strength, we're going to have the Debye length is going to be less. The reason is these particles, when the ionic strength is high, they're going to compress each other. Because of the high ionic strength, they're going to bond with each other, and the bilend is going to be smaller because these particles are connecting with each other with a strong ionic strength, strong ionic bond. But if the ionic strength is less, the bilend is going to be higher because these molecules are bonded loosely with each other in respect to each other. So as we increase the ionic strength, we are compressing the bilend, and therefore the size that we get from the dynamic light scattering is going to be less. One example is if you have your particles suspended in a salt solution, because a salt solution has a high ionic strength, the diameter that you're going to get, the diameter that is going to be measured is smaller compared to a particle that is being dispersed in water, because water is less ionized than a salt solution, and therefore the bilend is going to be thicker, and the diameter that we get from this particle is going to be higher. So we have to take into consideration the ionic strength. As the ionic strength is going to be higher, the strength of the molecules that are compressing each other is going to be higher, and the diameter of this particle is going to be less. One other parameter is surface structure. This can also influence the hydrodynamic diameter, the size of the particle. For example, if this is our particle, if we have some absorbed polymer on the surface of this particle, and if the conformation is in a format that the molecules are sitting into the medium, that will also influence the diffusion speed. How this particle with what speed is moving is going to affect it. The shape, we can have like irregular shapes. This is going to give us a different hydrodynamic diameter. We can have like spherical particles, so this is going to be different. A particle that has irregular shape, they undergo random diffusion, and they will have different diffusion coefficient depending on which orientation these polymers or these molecules um, are sitting in. So let's take a look at the different components of the dynamic light scattering in more details. So as I mentioned, in this technique we have a laser that is a focused light. We are exposing this laser into our sample. The sample is a solution that we put in a cuvette. The cuvettes that we use, they could be disposable glass cuvettes, it could be quartz cuvettes, and it really depends on what type of sample you have. We even have low volume cuvettes that take 2 microliters of a sample, and that's when you have a very small volume of a sample and you want to measure the size distribution of particles. You don't have more sample. There are actually cuvettes that can include this small amount of small volume of sample. The standard cuvettes that we use is called a cuvette. We'll take 2 or 3 ml solution. As I mentioned, it could be glass, it could be a quartz cuvette, and also we have special cuvettes that will contain low volume of a sample as low as 2 microliters. 2 microliter is a very small amount of a sample, and that's when you have a small sample and you want to measure it with dynamic light scattering. So you have a solution, that's your sample. You have particles dispersed in this solution, and you shine a laser to the sample. These particles are moving and they're going to scatter light in all directions. And in one of these directions, which is the 90-degree angle, the detector is going to measure the intensity of the scattered light in 19°. So we have a detector here. This detector is a photon counting device. It's actually capable of counting individual photons. So that's why some of the times we call this technique photon coloration spectroscopy. But again, the dynamic light scattering is a more common name for this technique. So this is our detector. This detector is counting the photons that are scattered from our sample. And we do this measurement over time. So we have different time scales, which is, for example, nanoseconds, very, very short time scales in terms of nanoseconds, microseconds, and milliseconds. So we have a function of time. We repeat the process of the detector will actually repeat the process of measuring this scattered intensity over time. So what we get, what the detector will actually measure, the diagram is intensity, fluctuation intensity versus time. As you remember, we mentioned that these particles are in constant motion in the sample. So once they are moving, the scattered intensity of the light is going to be different over time. So the intensity is going to fluctuate over time. So the graph that we get is going to be similar to like this. Remember that we're going to colorate this graph and get the data of size distribution. As for now, this detector is giving us intensity versus time, and we can see that intensity versus time is fluctuating. This is because the particles are moving constantly. So we have a fluctuation of intensity versus time. So this information is going to be given to a signal processor. A digital signal processor that is going to correlate the information of intensity fluctuation versus time and will give us a graph that is the size distribution of particles. This is the diameter and intensity. And this process is called colorating. It is done by the colorator. So one of the most important things to know about dynamic light scattering is how the digital signal processor is going to colorate this data, the intensity fluctuation. So what does the colorator do? The colorator is actually the processor in the dynamic light scattering technique. That's why sometimes we call this technique coloration spectroscopy. And the colorator is actually colorating the data of intensity fluctuation versus time to diffusion coefficient. And as you remember, the diffusion coefficient was the parameter that we used to measure the hydrodynamic diameter in the Stokes-Einstein equation. So let's take a look at how this happens. As I said, we have a laser. We shine this laser to our sample, which has particles with different size. And we have a scattering intensity. This intensity measurement is done over time, is repeated over time. So we have intensity that is fluctuating versus time. Intensity of the scattered light, which is fluctuating versus time. Now with small particles, the intensity will fluctuate rapidly because these particles are moving fast. So we have a diagram similar to this. the fluctuation intensity versus time is changing rapidly. But if we have larger particles, we have a diagram similar to this one. And in this one, the intensity is fluctuating in a much longer time scale. Because the particles are larger, they are moving with lower speed. So I'm going to write here intensity will fluctuate rapidly and in this one intensity is fluctuating in a longer time scale. So the rate of fluctuation in the scattering intensity is determined by size. This is very important. The rate of fluctuation is determined by the size of particles. So in the dynamic light scattering, we have billions of particles suspended in a solution that they are constantly moving and their positions with respect to each other and with respect to the detector is constantly changing because they are constantly moving due to the Brownian motion. So in this case, we have a scattering intensity, which is our signal. We have a signal, which is the scattering intensity. But what the coloration does, the coloration will actually extract the time dependence of this signal. So in coloration spectroscopy, we are actually having a factor which is time. We have different time intervals that we are measuring this signal, which our signal is the intensity, the scattering intensity. So the coloration is actually a time analysis technique, and we construct time autocoloration function, which this has an equation which I'm going to explain. But let's take a look at the diagram of intensity fluctuation versus time and how the coloration, the processor is colorating these data to coloration coefficient. So actually the colorator will colorate the intensity fluctuation to coloration coefficient, and the coloration coefficient is the parameter that, as you remember in the Stokes-Einstein, is a parameter that we can use to measure the hydrodynamic diameter of particles. So let's say we have a sample, particles suspended in a sample, and we are measuring the size of these particles with dynamic light scattering. The particles are moving, so the intensity is fluctuating over time. We have a diagram of this similar to this. So we are detecting this intensity fluctuation in different time intervals. For example, in time 0, we are measuring this intensity, a scattering intensity. In time 500 nanosecond, again we are measuring the fluctuation intensity. These are very, very short time intervals. The next time interval could be, for example, 1000 nanosecond. We are measuring the fluctuation in the intensity over time. Now in time 0, these two graphs don't have any difference with each other. We are actually comparing the difference between the fluctuation intensity graphs versus time. In another time interval, which is 500 nanosecond, these two graphs are separating from each other because the fluctuation intensity is going to be different because the particles are moving. So we're going to have a graph similar to this. So this graph is different from the first graph. In the next time scale, again we are measuring the fluctuation intensity. Again it's changing. Let me show you with another color. So the colorimeter, the processor, is actually comparing these graphs which the detector is receiving in different time scale, and it will colorate them to another graph which is called coloration coefficient versus time. For example, in time 0, these two graphs are completely identical. In time 500 nanosecond, they're going to be different. Again, as time passes, these two graphs are going to be more different compared to each other. And we get a graph which is similar to this. Now with the Stokes-Einstein equation, we can correlate the coefficient, diffusion coefficient, to the hydrodynamic diameter. And get a graph, which is our final purpose is to measure the size distribution of particles. Here we have the diameter, and here we have the hydrodynamic diameter. Here we have the intensity. The graph is going to be similar to this one. And here we can see what is the actual size of our particles and what is the size distribution of our sample. The dynamic light scattering is a very common technique, is one of the first techniques that we use to measure the properties of particles, especially if you have a sample solution and you want to make sure that you have actually made nanoparticles, and if you have larger particles, what is their size distribution? Are they like micrometers, nanometers? And it's a very great technique that rapidly will tell you